So you're going to edit methods in the MassHunter instrument control software. You can do it in an offline instance, but it's not a great idea if there's an online one running. You want to load an existing method. Don't try to start from scratch. It'll be really frustrating and the odds of it crashing are pretty good. So I'm going to pick a method that I know run and I know works, and then I'm going to edit it. And then at the end, I'm going to go file save as, or you can even do file save as in the beginning, or save method as. Okay. So to edit the method, we're going to hit edit entire method. But for most of these windows, we're just going to say OK, because these are parts of the instrument that we don't really need to worry about control over. This is basically getting injected and things like that. Every once in a while, you might change the washes and stuff. For the most part, you're just saying OK, 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 until you get to the main control window. When you get to this main control window, it's usually going to start on the most important setting, which is the oven. This is the temperature program. This is the temperature program. You edit the temperature program in this table, but you can also visualize what's happening with your temperature program in this plot. Specifically, the temperature is shown as the red line. The temperature over time is shown as the red line. You don't really need to pay much attention to the black dotted line or the green line. The green line represents the flow of the helium, and the dotted black line represents the pressure that's required to maintain that. The thing that you're by far going to change most commonly is going to be the temperature program in this table, and again represented as the red line in that plot. If we want to change how our chromatogram looks, how our things are eluting, we want to make things quicker, come out faster, or we want to slow down and try and separate peaks from each other, or things are getting pushed in a TM solvent peak, the temperature program is what we're going to mess with. So if we zoom in here, first thing, if we're just running one thing or a couple of things that elute closely, things will go a lot faster for us if we just run an isothermal. Don't run a gradient when you don't need a gradient. So for example, if I knew my thing came out in a gradient around 180 or something like that, I might just do a 150 isothermal. In this case, I programmed it, so it's just going to hold 150 for 8 minutes. So I just have one line, I put in 150, and you can see in the chart, it's pretty boring. It's just 150 for 8 minutes. If I want to run a broader temperature gradient, but maybe I have a couple things in there, but one elutes fast and the other one elutes much later at a much higher temperature, I could start at a low temperature and then ramp up to a really high temperature. And here I've set it to 15 degrees C. That gives me a total run time of 23 minutes, which is a bit of a long time. If I want to be really aggressive about it, I can increase my temperature rate, and that's going to shorten up my run time. But if I have two things that elute close to each other, it might kind of push them together. That is the typical tendency. And I can get even more complex with these gradients. You can sort of change the rate to try and pull peaks together or separate them apart. And if you have a broad swath of analytes that you want to look at, you can make all kinds of different gradients here. The lower you set the rate, the temperature rate, the more it's going to kind of tend to spread peaks apart generally. The lower starting temperature, you're going to get things that might be shoved into TM coming out, and the higher the starting temperature, things are generally going to come out faster. You can even sort of put in two ramps. This is actually the default Clark's method. For example, here I just programmed in this double ramp method where I start at 70, slowly move up to 150, and then from 150 I hold, and then aggressively move up to 320, pretty quickly. So this guy's not as long as one of those other methods, but should capture a ton of analytes, just an example. Some of the other things you can mess with, don't mess with the column here, but under the column there is the helium flow rate, which is set at a mil per minute. That is the best default. On the GC-FID, the FID can handle a higher flow. You can change that to a higher flow rate if you want. That generally does not do a whole lot, but really the only thing you want to mess with on this page is the flow rate. This inlet temperature, that is significant. It's set at 250. If you go higher, sometimes that can give you better results for less volatile things, but you're more likely to see thermal degradation when you go up higher. We're running a split right now. We could set this to splitless, but really you almost certainly want to be set for split for everything we do. We are at a 50-to-1 split. It's very common to change this split to go lower if you're seeing tiny peaks, and generally we're going to go higher. I mean, 100-to-1 is good. Some places run 200-to-1. The FID should be on. That flame should be on. And that under this signals tab, you need to make sure that save the data box is clicked. You don't want to make a new method that's unclicked by default. and you'll lose it. So when you've programmed everything you want, you're going to go ahead and click OK here. You don't really need to mess with any of this other stuff. You OK through this. Yes or no doesn't really matter there. And then remember to give it a new name. Don't save over your old method. And what I would encourage you to do is after every method and data file and sequence you do, just put your initials or your name as part of it. That will help to avoid a lot of confusion with data files later. If everyone has a file named atropine, that's trouble.